Hello, everybody, and welcome to Telescope Talk Pro, a weekly hangout dedicated to discussing the latest discoveries, science, equipment, and observatories in the world of professional ground-based astronomy. My name is Tony Darnell from deepastronomy.space, and today's hangout is one I've been waiting for a long time. We are going to learn about the Event Horizon Telescope, a worldwide collaboration that is connecting observatories from all over the planet to create one Earth-sized telescope that is designed to do one thing: to directly image the event horizon of a black hole. I know. That's right. Directly image a black hole. That's specifically the supermassive one at the center of the Milky Way called Sagittarius A star. Now, today's guest is Geoff Bower. He is one of the founding members of the Event Horizon Telescope. He's also a chief scientist for Hawaii operations at his institute, and he will tell us all about this amazing project. But before I start, I need to mention that the Telescope Talk Hangouts are sponsored by OPT Telescopes, a world leader in telescopes and accessories for both amateur and professional astronomers. If you need a telescope, or if you have a question, or if you need an eyepiece about just about anything, or you just want to talk about telescopes and astronomy with somebody who is just as passionate as you are about the night sky, then reach out to them at the link in the description box below and tell them Tony sent you. So my co-host for Telescope Talk Pro is Christian Reddy from Launchpad Astronomy, a collaborating YouTube channel that we are also streaming this hangout to. So welcome, Christian, and let me bring you up as soon as I can find my cursor. There it is. Hi, Christian. How you doing? Oh, yes. I see you're in the spirit. We can't hear you. We can't hear you, Chris. Are you muted?
Welcome back to Launchpad Astronomy. I'm Christian Reddy, your friendly neighborhood astronomer, and you are live on Telescope Talk Pro, where we take astronomy seriously.
Very seriously. That's right.
How exciting is this? We are now embarking on an opportunity. Well, rather to kind of back it up a little bit, just for my viewers, we have talked at great length about black holes on this channel, and we talk about black holes all the time in physics and astronomy, and it's great to talk about black holes. We've seen tremendous evidence for black holes. We've never actually seen a black hole, and that's for good reason, because black holes are by definition black. They swallow all of the light that falls into it. So how does one actually see a black hole? And the short answer is you don't, but you see what is immediately surrounding, or rather see the shadow of the black hole. And for the first time ever, astronomers are in the process of doing just that, taking an image, as Tony said, of the event horizon of a black hole. So I'm super excited to welcome our guest, Dr. Geoff Bower, project scientist for the Event Horizon Telescope. And welcome aboard, Jeffrey. It's great to have you.
It's terrific to be here. Thanks so much for the invitation. I'm really excited to talk about our project.
Well, that was my dog.
That was your dog.
Someone just showed up.
Guest, not my dog.
Yeah.
Oh, it's Tony's dog.
Yes. One day of these hangouts, I'm going to have a Panther cam. That's the name of my dog, Panther. So anyway, all right, Jeffrey. All right. So you work in Hawaii, but you're a member of the Event Horizon Telescope collaboration. Can you describe a little bit about I mentioned it in broad terms, but maybe you could talk a little bit about what exactly you're planning, what the goal science-wise of the Event Horizon Telescope is supposed to be.
Sure. So as you said, the Event Horizon Telescope is a global collaboration that makes use of telescopes around the world. And our goal is to make the very first image of a black hole and have the most definitive proof yet for the existence of black holes. And so we're using a technique called radio interferometry that we use to combine together these telescopes around the world and do something that no one has ever done before.
So when we talk about imaging, I mean, like Christian said, black holes are black. So is the goal here, when you say the event horizon, are you looking for like a real delineated boundary between things we can see and things we can't see? And will we see the entire thing or just a portion of it? What's the expectation? Help us visualize what we'll see.
Yeah, so we're not going to see the black hole. and we should be precise in how we talk about this. What we're going to see is the light that's emitted from just right around the black hole. We're going to be closer in than anyone else has ever gotten by about a factor of 1,000 in terms of imaging the effects of a black hole. And what we're going to see is the light from the very hot particles that are falling onto the black hole, maybe being ejected out of the black hole. And these particles are super hot because they've accumulated all that gravitational potential energy as they fall down onto the black hole. And so they radiate very efficiently, producing lots of light, lots of radio waves. And what we expect to see is the effects of strong gravitational lensing caused by the black hole, because we're in this weird domain of the black hole's gravity in very close proximity, so the strong gravity of the black hole.
Now you sent me several visuals. Would you like me to show that that MP4, the video, or was it?
Yeah. Let's show that right now. Go ahead and cue that up and play that.
Okay, it's playing right now.
So that this image is this is a theoretical image of what we expect to see. So this is a movie, and it's meant to convey how the source might change over how the black hole and its environment might change over the course of a few hours. And so that ring that you're seeing, that is what we call or we say we're seeing the shadow of the black hole cast upon the light that's emitted from right around the black hole. And so that ring that you're seeing there,
the well-defined one up front.
Right, the well-defined one is very strong prediction of general relativity that ring should be present there. That all the light is getting focused into that ring. We call it the photon ring. It's where the light is escaping from the black hole's environment to us and being focused towards us. And that and that ring, the really amazing thing about that ring is that it's actually very simply defined by the black hole. It has a diameter that's just about 5 times the diameter, or the Schwarzschild radius. And so the Schwarzschild radius is just basically the size of the event horizon, the region beyond which all light cannot escape. And so that ring is very well defined. It's predicted by general relativity. So our very first goal is we want to see that ring when we look at the black hole in the center of our galaxy and at other black holes in the centers of other galaxies.
And you said this was the photon ring?
Yeah, that's right. So it's the region it's just outside the photon ring. So the photon ring is where light, the boundary at which light can't escape. But just outside that is the ring where light can escape to us from the black hole's environment.
So light can approach this ring, and if it goes just a smidgen past it, it's trapped. But are these photons in orbit, or are they just being gravitationally lensed in this picture?
Well, so some of these photons will actually have been in orbit around the black hole, right? So we're in this regime where space-time is bent, and so some photons will go around and around and around the black hole before they finally escape and come to us. And some will be on a more direct path where their trajectory is just bent by the light, but they don't make a complete revolution around the black hole.
And the asymmetries in that we're seeing, is this based on material falling in, or why is it bright on one side and not so bright on the other?
Yeah, that's a great question. So the brightness, the enhanced brightness on one side that you see relative to the other side is a prediction of special relativity. And it's basically it's what we call Doppler boosting. So that material, we think, as it falls in, it forms into a rotating accretion disk, or a flow that goes around the black hole as it's going in. And the speed of that gas as it's falling in is approaching the speed of light. And just as the ordinary Doppler effect works, where you get a higher frequency signal that comes to you when something's approaching you, we get more intense light in the part of the accretion flow that's coming towards us, as opposed to the part that's going away from us.
But so this is not then an accretion disk.
Well, it's one of the remarkable things is that we think that an accretion disk must form, but one of the remarkable things is that what we expect to see is actually not that dependent on exactly how the gas is structured around the black hole. There might be a thin accretion disk. There might be a kind of quasi-spherical accretion flow where gas is coming in from all directions. And there might also be a relativistic jet that's present there. And as long as this emission is being created really close to the black hole, within a few to maybe 10 times the Schwarzschild radius, then we're going to get this ring.
Okay, so this is what we expect to see. Now, can you remind me again the wavelengths that we're going to be looking at? You said it at the top.
Right. So this is radio astronomy, millimeter wavelength radio astronomy. So we're right now, the experiments we're doing are at a wavelength of 1 millimeter. So I can't really do that with my fingers, but I can get close. So that's it's light with a frequency of 230 gigahertz, or a wavelength of about 1 millimeter. And the reason,
oh, I'm sorry. Go ahead. Continue, Geoff.
Well, I was going to say there are a couple of reasons that we want to work at this wavelength, and one is that our black holes tend to be very bright at these wavelengths. The other is that the technique that we're using, interferometry, we get more and more precise measurements the shorter the wavelength. And we'd love to do this experiment in the optical or the X-ray, where the wavelengths are very, very short. But technologically, that's not possible right now.
So this is a combination of what's possible. You're basically trying to do the best with what the current state of the art allows us to do.
Exactly. We're on the bleeding edge of interferometry technology to go all the way to 1 millimeter wavelengths.
And do you think you could tell us a little about what it means to do interferometry? I think one thing I always try to tell my students is that, we can do a lot with radio telescopes, but because the radio waves are so physically long, as you point out, it's very difficult to get very high resolution images that way. So how do you do that? How do you produce the kind of resolution you need at radio wavelengths?
Sure. So you're exactly right. So a basic fact that I'm sure you've taught your students, Christian, is that the shorter the wavelength, the higher the resolution, and the larger the diameter of your telescope, the higher the angular resolution. And so in the optical, you build a bigger mirror, and you get a higher angular resolution. And the same thing is true at radio wavelengths. We build a bigger antenna, and we get more angular resolution. But because the wavelengths are so large, even a millimeter is a very large wavelength for light. we physically can't build our telescopes as big as we need them to be in order to be able to get the resolution that we want. For your technically minded listeners, we're getting an angular resolution of about 20 micro arc seconds, so a typical seeing with a ground-based optical telescope might be 1 arc second. So this is 50,000 times more precise than that.
And that's and that's due to a combination of both the wavelength that you're using and the diameter of the telescope.
Exactly.
Okay.
Exactly. So we'd like to, in order to get that angular resolution at the wavelength where we're working, we need a telescope that is the diameter of the Earth. We need an 8,000 kilometer telescope. Now, I would love it if our funding agencies would just give us the money to go and build a giant telescope that would shadow half the planet. But that's not really practical. So, well, go ahead.
Well, I was just going to say what we did do, though, is you've put together several telescopes throughout the planet, and you've tied them together, right? That's what the Event Horizon Telescope does.
That's exactly right. So the Event Horizon Telescope ties together telescopes that already exist in some of the best observing locations around the world, and we tie them together. And the separation between the most distant pair of telescopes is what sets our angular resolution.
And I'm showing I'm just so you know, I'm showing the graphic called EHT Array right now as you're talking. So
yeah, so this graphic shows our network of telescopes, and let me pull it up just to make sure I'm talking about exactly the same thing you are, right? So you can see our global network here in this image. We have telescopes where I'm located in Hawaii. We have 2 telescopes on the mountain of Mauna Kea, the submillimeter array and the James Clerk Maxwell telescope. We have a telescope on Mount Graham in Arizona, the submillimeter telescope. There's the large millimeter telescope in Mexico, the Greenland telescope in Greenland. 2 telescopes in Chile, the ALMA telescope and APEX. And there's the South Pole telescope. And we also have 2 facilities in Europe that are contributing. One that's shown here in Spain and another in France that will be joining us next year in our experiment.
So effectively, this is a telescope with an effective aperture or diameter the size of the planet, correct?
That's right. So effective diameter, the size of the planet, but effective area, much, much smaller, right? So it's basically a mirror that's almost totally missing. You can think of it as just a mirror, but where we only have the pieces of the mirror that where the individual telescopes are located. And so even though that's a really flawed mirror, we're able to work some algorithmic magic and actually construct an image from this data.
And let's talk a little bit about how they're connected then. So this is while it's physically large in diameter, it's not a complete mirror. It's got holes all over it because the only resolving elements are the bits where the apexes of these lines come together. And so, but every one of these telescopes is looking in the millimeter range. These are radio telescopes, like you said. And one of the most important ones, as I understood it, as I've been reading about this, has been ALMA. ALMA is the Atacama Large Millimeter Submillimeter Array in Chile. It is one of the most oversubscribed telescopes in the planet, but it's a very high-resolution radio telescope. So does that mean that even though the mirror is mostly missing, like you point out, but some of the elements are really doing a good job getting some good data, right?
Yeah, absolutely. So the introduction of ALMA into our project has really transformed what we're able to do. So your viewers can see the picture of ALMA that's beneath the globes here, and it doesn't fully convey just how massive ALMA is. ALMA consists of 50 individual telescopes, 12 meters in diameter, about 40 feet in diameter. Many of our individual stations only consist of a single antenna that is smaller than one of those antennas. So we have a massive amount of collecting power there at the ALMA site, and that gives us incredible sensitivity for our network, and has really changed the game for us in terms of what we can do.
Okay, I want to talk a little bit about how these are connected, and then I want to get to some questions. So give us some idea, how do you connect all of these telescopes together? What's the process?
So the other technological miracle of this, the telescopes are one technological miracle, and the other technological miracle is the digital signal processing that's a part of the digital revolution that we're all experiencing, that powers our iPhones and the computing in the cloud. We record at each station vast amounts of data, and we're recording data at a rate about 1,000 times a fast home internet connection. So we're recording data. Wow. Currently at a rate 64 gigabits per second.
In the radio frequencies.
In the radio frequencies. And we have giant banks of disk drives. And we're writing that data directly onto those disk drives. We have in each station we have a bank of either 4 or 8 of these recorders, and each of those has a cartridge which has 8 terabyte hard drives in that cartridge. And when we're done with our 5-day experiment, we have filled up all of those disks. So we're recording
in 5 days.
In 5 days.
5 days worth of data will completely fill up all your storage.
Exactly.
Wow.
So we collect hundreds of terabytes of data per station. Mm-hmm. And then we use the most efficient data transfer method known to man, Federal Express.
I thought you were going to say UPS. Okay, Federal Express. I was going to ask, that was going to be my next question, and you've already answered it. I imagine this is just there's just too much data. You're just not going to be able to send it through the interwebs.
Even gigabit speeds aren't going to get it to you in any kind of timely fashion, is it?
Exactly. And so that's why we have this great technology of recording directly onto the disks and then sending it in. Some of our sites are incredibly remote, right? So we're observing from the South Pole. We're observing from Greenland. When we observe from the South Pole, we have to wait until winter is over in the South Pole just to be able to ship the disk drives out, because there's no way to get out of the South Pole in the middle of the Antarctic winter.
May I ask? You said that it was 5 days was enough. Was all that would fill up your storage. So is that pretty much how the observations went down? Everybody took 5 days worth of data, and now you're just trying to combine it all?
Yeah, that's exactly right. So we do annual campaigns, usually in the spring, March or April, and we set up about a 10-day window in which we'll take 5 days worth of data. And for all of that to work, all the telescopes have to be working. We have to be coordinated to nanosecond time scales between those telescopes, and we have to have excellent weather at all of these globally different stations around the world. And when all of those conditions are right, we say go, and everyone works in lockstep, observes for 12 hours throughout the night, and then the long process of analyzing that data begins when the experiment is done.
Okay, so I didn't realize you had to take simultaneous data. I thought maybe, some observations could be made on different nights, but no, it all has to be done in one go.
That's right. So for the interferometry to work, we have to. What we're doing is you can think of interferometry as a time delay experiment, that we're catching the same electric field, electric vector, electromagnetic wave at one telescope and at another telescope, and then we measure we know that they're going to arrive at different times because the telescopes are at different positions, and we know roughly where we're looking, but slight delays in the arrival time between the two stations gives us really precise information about just where the light is coming from. And then by having all these different pairs of antennas, each one measuring a different time delay, we're able to reconstruct an image out of that information.
So can I show your interferometry diagram? Does that?
Yeah, absolutely.
Yeah, that sort of shows what you're talking about a little bit, right?
Yeah, right. So this diagram. So we start on the left with the theoretical image, the ring that we want to image, and then we have our network of telescopes. And every time we add one new antenna to our network, we increase the power of the network by n antennas, because it's pairs of antennas that matter. When you just have two antennas, you get one pair. When you have three antennas, you get three pairs. When you have four antennas, you get six, and it keeps on going up like that. Now, so the plot in the middle is where it says measurements. That's the part of the mirror that we're filling in. And each trace that you see, they're elliptical traces or parts of ellipses. Each one of those traces is a pair of antennas, and we're watching the same source as the Earth rotates, and we get different angle on the source as the Earth rotates, and that's what causes those traces. So we put together all of that information. We make measurements of those time delays at each point along each of those tracks. And then we use some really sophisticated mathematics and image reconstruction approaches and turn those measurements into an image. And so you see on the right a realistic looking image of what we might get from an actual experiment.
Wow, that is so cool. Look at that. I love that. I mean, it's just amazing.
Yeah. And I just wanted to ask, just to clarify, because earlier we looked at some simulations, but I think what we're seeing here, the reconstruction on the right-hand side of this image, that's kind of what we're looking to. Is that this is closer to what you're expecting to see?
Yeah, that's right. That's right.
Cool.
So the image on the left here and the movie that we showed earlier are a theorist's vision of what's happening there. And then the image on the right is the experimenter's vision of what we think we can achieve with the current technology.
Wow.
And the current array.
That's amazing.
Yeah, it really is actually. It's and let me say we've been studying the black hole in the center of our galaxy, Sagittarius A star, the astronomy community for over 40 years. And up to now, all we've seen is just a fuzzy blob. And we've measured its properties very precisely, but it's just a fuzzy blob. the dream of getting to make this kind of image of it is really thrilling, really transformational in terms of how we see what we're doing.
Yeah, I agree. I mean, I'm looking at this and I'm getting chills just thinking, wow, what if it really does look like this? I can also imagine people, who wouldn't have any context around this might think, well, how come it doesn't look like the thing in Interstellar? And I think I know what I would say to that. But what would you say to that? Well, it doesn't have that glowy thing that we saw in Interstellar. What's going on?
Well, let me first off then say that what they produced for Interstellar is terrific, and it's actually based on real simulations of that incorporates lots of the physics that's going on there, and supervised by the great Kip Thorne, who's one of the leading theorists of general relativity of the past century. What we're seeing is different. It's been there's the filter of the actual observation, right? And that this is the unfortunate reality of not having infinite resources, is that we don't get infinite resolution. We don't get to see all the little details. But many of the things that you see in that interstellar image, where it's sort of half an arc and then an arc that kind of cuts across it, a crescent shape with an arc that cuts across. Some of the models predict that we will see that, and if you think about the movie that we showed earlier, right, that did have that arc that bisected the ring, and there are some details like that are dependent on just the details of how the particles are arranged and the light is emitted, just where it's coming from around the black hole. The ring is a feature we're sure should be there, but there are other features that will depend on the messy astrophysics of what's happening very closely.
Mm-hmm.
So when you said earlier that we were able to detect, the best we were able to do in the past was to get a fuzzy blob when in studying Sag A star, was that what wavelength? Because I know Chandra has done a lot of images of the Chandra X-ray Space Telescope has done a lot of views of the center of the galaxy. But what were the other wavelengths in which it was a blob?
Well, so at radio wavelengths, so Sagittarius A star was discovered at radio wavelengths, at very long wavelengths. It was discovered at, I think, a wavelength of 20 centimeters. So, wave about that big, about 40 years ago. And people immediately said, oh, that's probably the black hole at the center of our galaxy. And so in the wavelength regime between 20 centimeters and 1 millimeter, as the technology has improved, we've been marching along and going to shorter and shorter wavelengths and making higher and higher resolution images. And we actually see a remarkable thing, that it's this consistent fuzzy blob. And it turns out that's the result of scattering by electrons that are along the line of sight that kind of blur out the image.
That's where I was hoping we'd go. So yes, one of the things, the center of the galaxy is very difficult to see at certain wavelengths. Yeah. Visible wavelengths, we can't see at all. There's too much junk, gas, and dust and stuff in the way. But at certain wavelengths, we can become opaque. The very high energy wavelengths, they tend to go right through, and the very low energy wavelengths, like what we're talking about here. So this is why, folks, we have to kind of box in where we can see this black hole.
That's exactly right. This scattering phenomenon is, sometimes we feel a little bit like, nature has conspired against us, that here we have this beautiful black hole, it's close to us, and yet there are these electrons that are along the line of sight. They're not really likely associated with the black hole itself or anything near the black hole. They're just along the line of sight. But as radio waves hit those electrons, they get jumbled around, and it blurs out the image. That effect weakens dramatically as we go to shorter and shorter wavelengths. So that's another reason why we've gone to the shortest wavelength possible to do this experiment, in order to get the weakest amount of scattering interfering with our observations.
Okay, so all of you radio astronomers have come together from around the world. You cajoled and you talked and you begged everybody, let's be a part of this observation, join in, point your telescopes and coordinate with us. And you've managed to, over the course of the days that you've made your exposure, you've taken your data. So where are we now? I think, as I understand it, your data are taken, correct?
Yes.
And now what are you doing?
Okay, so
because we want to see this thing.
No one wants to show it to you more than I do.
Where's my black hole?
I mean, it's springtime in the Antarctica now, so you should have the data.
Come on, man.
There's no more excuses.
Don't just stitch them together in Photoshop. Come on, man.
Yeah. So we've had 2 campaigns now with ALMA. So spring of 2017, spring of 2018. And we have in addition to having a global
spring
array,
at ALMA or spring up here?
North American spring.
Okay, North American spring.
So, okay.
April 2017, April 2018.
Got it.
ALMA autumn, basically.
Yes. Yeah. And so we have. So it takes, because of getting data from all the sites and all of that, it takes about 6 months after the experiment before we've actually really assembled all of the data together. And then we have, in addition to a global array of telescopes, we have a global collaboration of about 200 people who are working away very, very hard on analyzing this data. So a very special computer that we call a correlator that combines together the data from each of the telescopes in each of these baseline pairs. We actually have 2 of those. We have one in Germany and one at MIT that process the data independently. And then we have a huge task of carrying out this sophisticated algorithmic inversion of the data that goes from the incomplete mirror to an image. So we're pushing very, very hard on that stage of it right now. And I can tell you we have some really great results. I cannot tell you what they are.
So you've got some tantalizing views.
We have some really terrific results, and I will become an ex-member of the collaboration if I tell you what they are.
I know we don't want to get you in trouble.
But actually, Geoff, we can help you, because you may need some way of announcing this to the world, and I think I can speak for Tony when I say that you are welcome to announce it to the world on this show. We would love to have you back.
Let's do that. That would be awesome. What would that be?
I mean, I know that our audience would appreciate hearing it, and
just keep that in mind.
I would love to.
I'd
love to come back. But I can tell you that we're anticipate something soon. Is what I will tell you.
Okay.
Okay. Well, I was going to ask, first quarter, second quarter, but soon.
Yeah.
We'll just take that.
Yeah,
we'll take that with the optimism. We do have a number of questions in both of our chat rooms, Tony.
Sure.
And I thought maybe we could start.
Let's do it. Yep. I just wanted to get to the status of where they were, and now I'm ready. So let's start asking questions. Go ahead.
Well, okay. I'll go ahead and start with a question. A couple of questions, one question of mine. We'll do one from yours, Tony. So I think Ask Questions, Try Stuff was asking, could it be possible to do a similar experiment, or maybe the very same thing with a series of smaller radio dishes spread over, filling in a lot of those gaps between the observatories that we have? I'm really paraphrasing the question, but do you want to go ahead and speak to that? Is that possible, or is that practical?
Absolutely. We're very interested in expanding our array, in filling in the gaps in our mirror. And because we have ALMA, which is so much more sensitive than all the other stations, and the sensitivity on a baseline pair depends on the sensitivity of both telescopes together. So we are actually quite interested in putting telescopes in other locations around the world. We're interested in putting telescopes in space that we can connect to from the ground, or that even are working space to space. So more than one telescope in space that are connected with each other.
We have weather problem that way.
Yeah, exactly. So you get out of the atmosphere, you can always observe, and you would continuously observe if you did that.
Fantastic.
The real challenge is there are two challenges. One, of course, is money, and then the other is finding good weather locations around the world. One of my colleagues in Europe is working very hard to find a location in Africa that will be a good location for a telescope. And there's a location in Namibia that looks like it's good. It's not as great as Hawaii or Chile or the South Pole, but it's a good site. And so we're looking for sites like that.
Okay, well, guys, as most of you have noticed, I have the ability now to look at chats from all of the different platforms we're streaming on, which is YouTube, Facebook, Twitter, and Twitch. And I'm looking at all of those now. I put a real crude scroll bar here. I'll make that better for next time because I only just now started playing with it. But I'm looking at all I can finally get it all into one spot, which is nice. Condor Boss on YouTube is asking, I've heard they already have an image, but they haven't verified and checked yet. When is the image due out? We just answered that. It'll probably be hopefully in the next quarter or so. And Simon Farmer wants to know if you've seen it, and you said that you've seen parts of it, right?
Yeah. So let me say we had a collaboration meeting in the Netherlands in early November, and it was one of the most intense weeks of my life. We had 120 scientists and engineers, students, working very hard on this data, and asking a lot of tough questions. We're making sure that we make no mistakes with what we release to the public and what we release to our scientific colleagues.
Well, yeah, but I appreciate that. And that was something that when you think of things like gravitational waves and LIGO, they had to be super careful about because they had a very low signal to noise. What is your signal to noise here in this technique? Is it something, is it a high, do you have a lot of signal, not so much noise? It's just a matter of getting it all, synchronized. What's the signal to noise like?
So the signal to noise it's difficult to define because we have different levels of it, or we have to define it carefully when we talk about that. So instantaneously on one of these baseline pairs, say especially a baseline to ALMA, the signal to noise of a detection within minutes is 100. So it's very robust. We detect the source very clearly.
That means the signal is 100 times greater than the noise.
Exactly.
Right.
The more complicated and difficult step is that sophisticated reconstruction that we do, where we have all of these different measurements, and we need to turn that into an image. And we have our measurements from our incomplete mirror, and that is the regime in which we're working to to be absolutely certain that we know what we're doing and we're not making any mistakes. And it's harder to quantify exactly what the signal to noise is.
Okay. Okay.
I think that dovetails into a question that was asked in my chat, Tony, but I think it'd be good to
go ahead.
Ask it here.
Say the name.
The question is, how real will the image be? And it sounds to me like, Jeffrey, that's exactly what you're trying to make sure, that it is in fact a real image and not an artifact.
Exactly. The image is real. This is, and it's as real as anything that you would take. You point your CCD at something that's a little bit more direct, but the image is quite real. And what we're not going to be giving you, an artist's interpretation.
Right.
We're going to give you an image that is a representation of the data.
A lot of people will be happy about that. So many artist representations. People get tired of those. So no, this will be real stuff. An actual image of an actual black hole event horizon. Go ahead and take Condor Boss's question down there. Are there any radio telescopes in space? A radio telescope a radio telescope on the moon help?
So there have been a few radio telescopes in space. There's one currently operating. It's called Radio Astron. It's a Russian project, and it goes out to extremely. It's on an elliptical orbit, and so it goes out to extremely long baselines from the Earth. I think 300,000 kilometers. And so that produces very high resolution images. It doesn't work at the wavelengths where we work at. It works at longer wavelengths. So we can't use it for our science, but we do have a vision of putting telescopes in space that will work at 1 millimeter wavelength or even shorter for our science. Cool. Telescopes on the moon, probably not really needed for this experiment. It probably just adds a complication to try to put it on the moon and be happy with it just floating out there.
Yeah, radio telescopes don't really suffer much, do they, from being under the atmosphere of the Earth?
So at very long, there are three regimes. So typical radio waves, 20 centimeter radio wave basically doesn't see the atmosphere at all, or sees it only a very little. 1 millimeter wavelength, where we're working, we're very heavily affected by water vapor in the atmosphere, which is why our telescopes are all in locations that are high and dry. So getting out of the atmosphere would definitely help us. And then the very long wavelength regime, where waves are 1 meter in wavelength or longer, those are affected by the ionosphere. And so getting out of the atmosphere would be a great help to them. And people have talked about doing that on them.
Okay, here's one from Simon Farmer. If Geoff could compare the target image to the Meerkat image produced this summer of Sag A star region, that would be awesome.
Okay.
Should I show that?
I actually put that Meerkat image.
You did? That's why I asked that question. Let me go ahead and put it up. It's up.
Asking. We happen to have a picture.
So I've got it up. So maybe explain what we're looking at.
Okay. So this is the really large scale image of the center of our galaxy. And, if you haven't been following radio astronomy, this probably doesn't look anything like what you think the center of the galaxy looks like, right? If you're used to optical images of the center of the galaxy, you're used to seeing stars and dust lanes. And what you see here is you see the plane of the galaxy that goes across the horizontally across the middle of the image. And that really saturated region in the center is where Sagittarius A star lives, but it's on a very, very small scale here. The scale of this image is probably 1 million times larger than the scale of our image. Now, I love this image because it's got so much great stuff going on in it. It's supernova remnants and star-forming regions and these really bizarre filaments, which are some kind of magnetized structures in the center of the galaxy. And the white points that you can see are background galaxies that we're seeing through the center of the galaxy. There are pulsars in this image. It's really, I'm really blown away by this image. I'm glad that everyone's getting a chance to see it.
Gary Wack, well, I'm sorry I can't pronounce your handle, dude, because where can I find this image? I'm going to make there's going to be a Google Drive folder. By the way, are the images that you've shared with us, can they be shared with others, Geoff?
Yes.
Okay. So I'm going to make that Google Drive link available to you in the video description after this hangout.
Yeah.
I didn't do it because I didn't get a chance to that, Geoff. And you can just download it from there. But you can also get that image elsewhere too, right, Geoff?
Yeah, absolutely. So I can steer people to eventhorizontelescope.org, which has a lot of information about our project and simulations and images. The Meerkat image, so Meerkat is a telescope in South Africa, a new radio telescope in South Africa. And so if you search for Meerkat and radio astronomy, you may get some cute pictures of little mammals, but you'll also get great astronomy pictures too.
Okay. Galaxia wants to know if you can tell us what you've seen in the image.
I cannot.
she's after some scoop here. That's go ahead. Do you have a question, Christian?
No, I was just going to ask. Well, someone's asking, will the picture have color? But just trying to find any grasping at any straws, right?
Well, I can address that. So, so what is color? Color is right is seeing things at different wavelengths, so we're seeing things in the color of 1 millimeter wavelength. If you like, that's a way to think about what we're doing. Some of the images that we will release will be released with a color map but that color map will represent intensity.
Right.
How white hot and red cool, that sort of thing. But we're not likely to produce images that represent true color in any sense.
Oh, okay. True microwave color.
This question is why I love doing these hangouts. This would Got Bread is on YouTube is asking, based on the angular resolution figure from before, I get around 24.3 million kilometers per pixel. The diameter of Sag A star is around 22.5 million kilometers. Does that mean the black hole only takes up around a pixel?
That's about right. I cannot verify on the fly.
These guys are sharp. I love these guys. They do the math.
Can't work it out in your head, man.
Good question.
But that is about right. That the black hole itself is about 1 pixel, and so we expect to have something like 10 pixels across the image. So it's not going to be like this Meerkat image where there are there's
all that stuff
pixels in this image.
Right.
Well, here's a good question from Simon Farmer. I'm curious about this too because I like GPUs. Would real-time on-site processing using GPUs extend the recording time? Because radio data isn't radio. I'm sorry, and then I'll let you answer. Isn't radio data well suited for that kind of streaming processing that GPUs do?
So the radio astronomy community is really big into using GPUs. We're also really big into using FPGAs, field programmable gate arrays. So we actually, which are kind of a one level of complexity higher than GPUs in terms of the difficulty of programming, but they're more powerful and more energy efficient. And so we do pre-processing of the data there at the telescope site with our FPGAs. But one of the cool things about our experiment, but also one of the things that makes it really difficult, I take you back to the mirror analogy that I gave you, right? And we're basically stopping light when it hits our mirror in Hawaii. And we're stopping light when it hits our mirror in Chile. And we're recording the electric field. We're recording all the information that we possibly can about that light. And then we put it on an airplane and we ship it to MIT or to Germany. And then we start the light again and play it back in our computer there. And that's the regime where high-powered computing like GPUs or large clusters or FPGAs also comes into play in a big way. Okay.
I'm not sure if it's Jan or Jan Dryak, but can this principle be used with optical telescopes, interferometry, he's asking, combining pieces of mirror all around the world?
It is. It can be done, but there are some technical limitations that make it very, very hard to do. So there, and to my knowledge, it has never actually been done.
Okay.
And there are a few limitations that make it very, very hard to do and not very sensitive. Now, interferometry, of course, began in the optical, famous Michelson-Morley experiments, in which on a single telescope they put an aperture mask and they just let light through two different holes in that mask and combine the light together from them and use that to measure the diameters of stars. And that technique is used locally. So where you don't record the electric field, but where you combine the light from multiple telescopes that are maybe within 10 meters of each other or 100 meters of each other, and you get better angular resolution.
Okay, I want to ask Ryan Korniloff's question and Simon Farmer's question together. So the observations from the Event Horizon Telescope, will it produce a single image and not an animation? And Simon's question was, are there future uses of this telescope? I'm sorry, Hans Milling, not Simon Farmer.
That's a great question about whether we get a single image or an animation. Our goal ultimately is to be producing movies of what happens in these sources. So Sagittarius A star, the orbital period of the innermost orbital period is about 30 minutes, and we observe it for 6 to 8 hours at a time. And so we do think that in the future we'll be able to see gas rotating around the black hole or features appearing and disappearing.
Wow.
Yeah, I know. It's super cool.
Yeah, I mean, I'm just
it's going to take a little bit more algorithmic wizardry than what we have right now to release that. I also want to mention that we actually have two primary targets. We've been talking about Sagittarius A star the whole time. We're also targeting M87, and actually maybe if you want to pull up that.
Sure, I got it. It's up.
And so this is M87 is a galaxy in the Virgo cluster. And its black hole is about 1,000 times more massive than the black hole in our galactic center. So this is the optical image, space telescope image. The white glow is all stars. Buried deep in there is the black hole in the center, and then you see a jet of particles that's in the blue that's being ejected by the black hole out of the center of the galaxy. M87, we will also want to make movies, but it evolves much more slowly because it's more massive. Typical timescales are 1,000 times slower, so days to years rather than tens of minutes to hours.
Okay, and I know we're out of time. That's why I'm trying to rush through this. What about the future projects? Are there any? And this is from Hans Milling about would the latest radio telescope in China have helped this if it were online?
The FAST telescope in China, terrific, very sensitive new telescope, largest telescope in the world, but it operates at a wavelength that's too long for us. So. Okay. Plans for the future, we're just getting started. We have so much that we want to see in these sources. We want to make images. We want to make movies. We want to increase the sensitivity of our array so that we can look at other sources. We want to see how these sources change over time. We want to push really hard and improve the quality of the images that we make and see if we can see effects that tell us about whether or not general relativity is true. So really stay tuned. There's a lot to come.
Great.
Well, I was gonna say we are just about out of time here. Actually, we're a little bit past time. We didn't even get a chance to talk about some of the science questions that you're hoping to answer, but obviously testing general relativity is high among them, right?
Yeah, that's the big enchilada here.
Relatively doesn't need any more tests. We've tested it passes. It's okay. It's all right. Just show me the black hole. That's what I want to see. The fact that there is one at all as a test is a good confirmation of Einstein. So
yeah, absolutely. Seeing the ring will and this is. Will be an incredible demonstration of general relativity and of the existence of black holes, and also I think quite visceral, right? That there's as Tony said at the outset, there's a lot of evidence already for the existence of black holes, but an image, just like that the astronauts, the moon landing astronauts, looking back at the Earth and taking a picture of the Earth from the moon. Everyone knew we lived on a globe with oceans and continents and clouds.
Well, most of us do.
Well, right. Some people are still not.
Fewer people today than back then. Okay. Yeah.
Right, but seeing the image is just that show. It takes you a step beyond.
Yeah. And no more inferring, right? We're going to see it directly. This is it. This is the black hole. No inferences. Well, all right. I'm going to have to cut it off there because we've moved up enough of your time. But here's what I recommend, Geoff. Perhaps early next year you might consider a revisit, and we'll go into the science questions of the Event Horizon Telescope and maybe dive into it a little bit more.
Geoff, like I said, the offer still stands. We'd love to give you a platform to announce your results.
Okay.
Nice try, Christian. But I think they're going to probably. I think he's got some channels in mind for that. The whole world's going to pick this up.
I'll be happy to come on and talk about our results.
You're a rock star.
We're shamelessly going for ratings over here.
Yeah, I mean, what are you going to do? You got to try what you can.
No, but Geoff, thank you so much for joining us. Yeah, I mean, I got to tell you, I'm listening to this, and Geoff, I'm just glad that you described that moment of seeing the globe for the first time. Especially, we're coming up on the 50th anniversary of Apollo 8. Wow, that was such a critical moment, I think, in humanity, and I think this is going to have a similar impact. So I thought that was a perfect analogy, Geoff. Thank you.
Great, thank you. Yeah, well, a real pleasure to talk to both of you and to your audience.
All right. Well,
always fun to do.
yeah, definitely fun to have you here. So I want to thank you very much. My guest today was Geoff Bower. He's one of the founding members of the Event Horizon Telescope, a worldwide effort to try and actually, not to try, but to image our black hole at the center of our galaxy and M87 as well. And the results are expected soon, early next year. We'll definitely be following up, hopefully, with new stuff. I want to thank you all so much for being with me on this new chat setup. Also, this is probably the last Telescope Talk Pro hangout for 2018. Christian and I will pick up again early next year with the schedule hopefully being filled out soon. So this will be the last one. I will be back with Future in Space on Thursday with Harley. That will be the last one of those for 2018. And I think Carol and I might be back the following Thursday with a look back at 2018. So that's what's coming up for Telescope and Talk and live hangouts here on Deep Astronomy. Thank you so much to Geoff Bowers for taking time out to talk with us. Thank you, Christian, for helping me co-host. I appreciate this. And please go subscribe to his channel, Launchpad Astronomy. If you haven't, the link is in the description box. So go check him out. He makes some nice videos.
Thank you.
All right, guys. Thank you all so much for watching. And as always, keep looking up.